Hello and welcome to this webinar in the 2021 Cambridge Festival, which as Josh said is given in partnership with Cambridge University Press, who employ me, David Trenard, to publish books in the general area of mathematical science. One of the books we're really pleased to be publishing in the next month or two is Compressive Sensing by Ben Adcock and today's speaker, Professor Anders Hansen. Anders is a Norwegian applied mathematician who holds a joint appointment in Oslo and in Cambridge, where he's a Royal Society Research Fellow, which means he's let off some teaching and admin so he can spend more time researching and writing his book. His research is in an area that's emerged during the last few years from two much older areas of mathematics, and it's called computational harmonic analysis, which basically is the theory behind modern image analysis. And it enables us to have crystal clear pictures from very weak signals. It's got lots and lots of applications, from medical imaging to environmental science, to biodiversity, to face recognition, to spacecraft roving about on Mars, and to Pluto flybys. He's currently using mathematics to understand why deep learning often doesn't work, despite all the hype you might hear about it, and how to make it better. So that's enough from me. And now, without further ado, over to Anders. Thank you, Anders.
Well, thanks very much, David, for the kind introduction. And I must say, it's a great pleasure for me to be part of the Cambridge Science Festival and to talk about one of the research projects that we are really happy about and engage a lot in my group here in Cambridge, and that is artificial intelligence. And I'm going to start the talk by asking you a very simple question. How do you recognize a cat? So if we take a look at this adorable little creature, how do you know that this is a cat? I asked my daughter this question, and she said, well, I just know it's a cat. But I asked her to elaborate on this and said, but if you were to tell me, why is this really a cat? She would point out that, well, there's something characteristic with the eyes of a cat. You have the pointy ears, the whiskers, the paws. And in some sense, there is a collection of different types of features that will allow us to say that this here is a cat and say not a dog. Now, the question is, how does artificial intelligence recognize a cat? And the purpose of that question is, I would like to show you a little bit what's going on inside the sausage factory of artificial intelligence. So to be able to do that, I need to put this in a historical context. Because if I had asked the question, how does AI recognize a cat 10 years ago, the answer would have been, we don't have any AI that can recognize a cat. So to put this in perspective, what I've shown you here are the scores of the winners of the ImageNet competition. The ImageNet competition was an annual competition in computer vision where one competed to become the state-of-the-art method for classifying images. So the competition would be as follows. You would have 1,000 classes of different types of images, like cats and dogs, but not just cats and dogs, but different types of dog breeds. And the challenge was to create an algorithm that could take the image or images as an input and tell you what is in the image. And of course, this is incredibly important in computer vision. I mean, if you want to have an automatic car, of course, you will need to have some kind of device that can see just like the human. But if you notice here, in the 2010 competition, this here is the failure rate, 28.2%. And in 2011, 25.8%. When you're pushing 30% failure rate, you can't really talk about having a product that can be used. This was more like an expensive hobby. There's no way that you can have an automatic car with a device that has a 30% failure rate and can't see the difference between a rock or a plastic bag coming towards your windscreen. But here is the magic number. The magic number is 2012. And this is where you can see that there is a substantial gap. This is where deep learning is introduced. Now, deep learning was a technique that had been around for a long time, but this was the first time when deep learning was able to beat any competitor in the ImageNet competition and get this incredible gap. And what happened was that the community, or the people in the community doing other things, well, they just threw whatever they had in their hands and started doing deep learning. And here you can see the rest is history. And it takes some extra years, and then one is actually has superhuman performance with deep learning for image classification. And this is unprecedented. And if you now look at the scores for the 2017 competition, all of the top 5 are essentially superhuman performance, and they're all using deep learning techniques. So what has happened now is that there's really a revolution. There's before 2012 and there's after 2012. And if I now were to tell you what is really going on, well, that is a very interesting question. And this is what we're going to spend some time on in the rest of the talk. So I'm a mathematician, and I'm actually going to show you mathematics here. And if you're not a mathematician, don't worry at all, because I will explain in layman terms everything that I'm going to be talking about here. The building block in modern AI, typically for image recognition, is what we call a neural network. A neural network here, I'm going to call it phi, the Greek letter phi. It takes in an X, which will be an image. And if we now have the task of figuring out if there's a cat in the image or not, this neural network will give you a 1 if there is a cat and a 0 if there's no cat in the image. Of course, this can be made much more complicated, but I just want to give you the very basics. Now, this neural network is composed by a whole lot of what we call affine mappings in mathematics. You don't need to understand what that is. You can think about this just as a collection of numbers. And the way that these neural networks are designed, these numbers make these networks so incredibly flexible that if you give me an image of a cat that I plug in, I can set these numbers in the neural network so that the neural network will spit out a 1 and say, yes, there's a cat here. But that doesn't mean that if I take another image and plug it in, that I will get a 1 and it says that it's a cat. But what I can do is that I can do this with many images, with cats and without cats. And I can now set the numbers here in the neural network so that for all the cat images, I'm going to get a 1. And for all the images where there is no cat, I get a 0. And miraculously, if I do this for a large enough data set, I can now take an image of a cat for which the neural network hasn't seen before. I can plug it in, and it will, with a very high probability, give me the correct answer, that there is a cat in it. And if there's not a cat, it will give me 0 with a very high probability. And that's what's going on. This is actually not mathematically that sophisticated. And the issue here is that we can do this training procedure, but when we're done with that and we've set the numbers, we really don't know very much else about what's going on. We know the mathematical object, but when we have created it, it is a black box for which we can only test afterwards. And that is a serious issue when we're going to try to understand what it really does. Because the truth is, we really don't know exactly what it does. We can test it, and it does remarkably well, but why and how, that is a delicate issue. And that's what we're going to talk a little more about. But I want to talk a little bit about the unprecedented impact that neural network has had on deep learning. And of course, since the 2012 revolution, when we now have this device that can literally take images and tell us what are in the images, that means that we can potentially use that in a lot of different sciences. For example, the medical sciences. And Geoffrey Hinton, who is one of the founding fathers of deep learning, and actually it was his group who was behind the 2012 competition and the big win there, he says they should stop training radiologists now. So radiologists are the doctors that will look at medical images, for example, from an MRI machine, and will tell you if you have cancer or not. And the idea is that if we now have machines that can look at images and identify them as well as humans, potentially even better, why should we spend resources on training radiologists? We should have a computer doing that. But things are not that simple, and we're going to get into the details a little later on the talk. But I do want to mention the issue here is really that we don't know a whole lot about what's really going on. And the issue is that modern AI is based on a trial and error approach. And because of that, we don't really have the foundations. And this has been pointed out by many people. Google's Ali Rahimi put this in perspective when he got the Test of Time Award at NIPS in 2017. And he likens modern machine learning to alchemy. And not everybody agrees with Rahimi in his assessment of that. Jan LeCun, who is one of the other founding fathers of deep learning, took serious issues with this. And for those who are interested, I highly recommend you that you Google this, because there's a very vibrant discussion afterwards. Anyway, regardless, if you agree with Rahimi or not, I think we can all agree that we can learn from the alchemists. And what the alchemists did was that they wanted to create gold. And the way they would do that would to take a pot, add a little bit of green, add a little bit of yellow, stir, and hope that they would create gold. Now, they wouldn't create gold, so you can iterate this process and say, well, I didn't succeed, but I'm going to add a little bit of red now, and then I'm going to try again. And you can continue this and add a little bit of brown, and then stir again, and continue and continue. The important thing is that that research methodology will never be able to discover its own limitations. You will never be able to understand that you cannot create gold that way, and you can never create gold at all. To be able to do that, you need a completely different foundations program. And that is what we're working on as mathematicians, to try to understand some of the bizarre effects that I'm going to talk about a little later on now with deep learning. And we're going to try to use mathematics to essentially show that there are methodological barriers on the things that we would like to achieve. I'm going to discuss that a little later. But I want to take Hinton's suggestion seriously, and I would like to ask the question, should we really stop training radiologists now? Now, a radiologist, which is now replaced by a computer, is actually not science fiction. Actually, having the automatic doctor is not science fiction at all. It's old news. And I want you to take a look at the date here, April 11th, 2018. That's almost 3 years ago. That is a very historical date. This is the first time that the American Food and Drug Administration permitted the use of artificial intelligence and deep learning in automatic diagnosis in medicine without any interference of a human clinician. It's deemed safe, and this is actually now legal to sell. So this sounds great, and it might also be great, but there are several questions. Now, this is for early detection of diabetes. This is not yet cancer detection or cancer diagnosis, but this is just the beginning. Now, when this press release was made and it was public that FDA had now approved this, then there was a paper in Science. Well, it was published a year after. It had to go through a review process. And many of you may know that there are two very important, or what should I say, prestigious outlets out there when it comes to publishing in Science, and that's Nature and Science. And this paper here was published in Science. And it's published by people who are not grumpy mathematicians like me, but people in the medical profession, the medical research profession. So this is a collection of people from Harvard Medical School and MIT. It's led by Isaac Cohane, who's the head of the Department of Biomedical Information at Harvard Medical School. And what they write about is a very interesting phenomenon, and that is what we refer to as instabilities in deep learning and artificial intelligence. And the main figure in the paper summarizes a lot of the phenomena that are important to understand. So the first experiment that one does is an actual cancer detection AI. And here the AI has been trained to understand if you have a mole that's benign or malignant. So you train a neural network on a lot of different images of moles that are either benign or malignant. And after the training process, the AI that has been created has an incredible success rate, which is very comparable and even slightly better than the human. But here comes a catch. Now, in this case here, the AI is very, very confident that this is benign. But you can add just a little bit to the image, a little noise, which is so small that a human eye cannot capture it at all. these images here completely identical to the human eye. Yet now the neural network and the AI is very confident that this is actually malignant. And that raises a lot of questions. First of all, what on earth is going on in terms of the reasoning? Why would the neural network be so confident here that this here is benign, but this image here, which looks exactly the same thing, is now super confident is completely the opposite? You can do a similar fooling, if you will. You can rotate the image, and then suddenly it goes from benign to malignant. Deep learning in AI doesn't have to be used just for image classification. It can be used also for text analysis. You can think about having an automatic doctor that would simply look at your patient history and say, well, based on that, I could say that you are in a low risk or a high risk category for a certain disease, for example. But what happens? You can take a sentence here for which you replace some of the keywords with synonyms so that the meaning of this sentence here and the meaning of this sentence here is very much the same for a human. However, the AI changes his mind completely. You could also do this, for example, in relation to an insurance claim. Suppose you file an insurance claim, typical for medical insurance. You list certain issues, and you now add a little bit of extra information that medically should be roughly the same, and now you go from denied to approved. And what this experiment suggests is that there is an inherent instability in the AI. And that is an issue that we're going to talk about a little further on, because we would like to understand how that affects the ability for us to trust it. Now, this paper here was written as a direct response to the FDA approval. They, of course, addressed other issues as well. I'm not going to read out the paper. What I do want to highlight is this quote here. An essential question remains when and how to intervene. So it is not something that is sort of looked upon lightly. This is a serious issue, and it's a serious issue in the debate. So, of course, these issues are very interesting for us in the scientific community, and particularly in mathematics, because we would like to understand, and we would like to potentially suggest ways to overcome the hurdles, or to realize if there's a methodological barrier here. So one of the key things that one does to try to understand really what the deep learning or the AI have learned is to try to give them bizarre images. And what you would hope is that if you gave neural networks and AI bizarre images, you would hope that they would have very low confidence in their prediction. So if you give a human something that they haven't seen before and you ask what it is likely they will say, I simply don't know. I have very low confidence in what this is. But what happens with AI is the complete opposite. All of these images here are given to an AI which is very high performing, and is 99.99% sure that this here is an armadillo, this is a jackfruit, this is a peacock, which of course is complete nonsense. Now, this is not random noise. They're tailored so that you get these bizarre phenomena. But the important thing is that we cannot really trust the confidence that the neural networks have, and this is because of this instability. Now, you can potentially understand why this becomes a baseball. You can sort of see the kind of pattern, but it's clearly not a ball. It's just a pattern that reminds you of a baseball. It's probably stretched to call this an electric guitar, but I can understand that this is a peacock. You can see the pattern that you can think about the tail of the peacock, but it certainly isn't a peacock. So what we can take away from this message here is that it is very hard to understand, and it's hard to trust exactly the output of a neural network, despite that on average it works very well. And this has become an industry now, and ways to fool AIs. I don't know how many thousands of papers there are on this subject now over the last 5 or 6, 7 years. I just want to highlight one of my favorites. This is called Deep Fool, and this is a software which is created by a fine group of researchers at EPFL. They wrote a very good paper about this, which was called The Robustness of Deep Learning, which is a little deceiving given that it's all about how unrobust it is. But the message from this is quite universal. The issue is that you can take two images that look exactly the same, but the neural network will give you very different output. So in this case here, the question is this a whale or a turtle? And to be honest, it's actually hard for me to tell if this is a turtle or a whale. I really don't know. But what I do know is that if I said that this is a turtle, well, then that is a turtle as well. Or if this is a whale, then that's also a whale. But what happens is that the neural network will give you different answer for what seems to be exactly the same thing for humans. And what they've been able to do with this Deep Fool software is a very fascinating phenomenon. They've been able to create universal perturbations that they can actually add to all images. And this universal perturbation, where if you add that, which is created for a particular AI, and if you add that to any image, now suddenly the performance, the success rate goes down dramatically. So the failure rate goes from, say, 3% without the perturbation. And if you add this, you end up with a failure rate about 80%. And what you see here are different types of these bizarre perturbations. And when you add this to the image, it's so small that the human eye can't see it. But it will now fool 80% typically of the cases. And you can even swap them. So you can create one for one AI, and then you can try it on another one. And then the failure rate may not be, say, 80%, but something like 50 or 60. And this suggests a quite universal phenomenon that you can actually use similar tricks to fool one AI, and you have never seen the other AI that you try this on, and it's still going to fool that. So what you can see here now, these are actually images for which a universal perturbation is added. It's very hard for the human eye to spot that there is anything going on here. But what you actually see is now that the Christmas sock becomes an Indian elephant, the guy in the ski mask becomes an African gray, and you have all of these nonsensical labels. So the big question is now, why does this happen? And I want to show you a mathematical theorem that actually suggests why this is happening. And it gives us an indication that this is a methodological barrier, because the paradox of the theorem that I'm going to lay it out in layman terms for you. What this theorem here says is that it's the methodology that gives us the instabilities, despite the fact that there exists a very accurate and completely stable AI, but we don't know how to construct it. So what this theorem here says, and I'm going to explain in layman terms what it does, it says the following. There are uncountably many functions or questions a la, is there a cat in the image? And uncountable means just infinite and even worse than that, even more vast than infinite. And what it says is that there are a vast collection of them for which you will have the following phenomenon. You can choose an epsilon, a number, which can be arbitrarily close to zero. And the closer it is to zero, the more unstable we're going to make it. Now, this epsilon has to be less than 1 over k plus m. And k is going to be the number of training data that we use to create this AI. And m is going to be the number of test data, because we're going to test it as well. And m can be arbitrarily large. And now what happens is that there are now uncountably many different types of training data, and also uncountably many different types of classification or test data that I can test this on. So if I now actually train my neural network, this here is just math mumbo jumbo for saying I'm training my neural network. What will happen then is that the AI, or the neural network that you'll get, will be perfectly successful on all the training that is done, and all the test data as well. So it will have incredible success, just as we see in practice. But there will be uncountably many cases for which it will misclassify. And these cases are going to be epsilon away from the training data that is already seen before. And that epsilon could have been arbitrarily small. So this is exactly what we see in practice. You take two images that you cannot see the difference, but one of them will be misclassified. And there's uncountably many of them. Now, this is not the paradox. The paradox is this: that there exists another AI, another neural network out there, which is as successful and also completely stable. This here is math mumbo jumbo for saying that it's stable. So what's happening here is that we're getting the bad guy, but there exists a good guy. And why we're getting the bad guy, it is because we're doing the training process like this. This is a methodological barrier. It is the way that we're actually training them. That is why we're getting the instability. And it's not like we are occasionally getting the bad guy, and most of the times we're getting the good guy. No, we're always getting the bad guy. We don't get the good guy, and that's the crucial issue. And what this theorem suggests is that there is a mathematical reason for this. There is a methodological barrier. And that means that if we're going to resolve the instability issue, we need to have a completely different method to be able to get the good guy. And that is an interesting observation. Now, whoops. Now I'm going to change gear a little bit, and we're going to talk about medical imaging and artificial intelligence in medical imaging. You see, the human vision system is great at looking at things, but it can still not see inside things. It cannot see inside of the human body, for example. For that, we need medical imaging. So what I've shown you here is a magnetic resonance imaging scanner, an MRI scanner. Some of you may have tried it. The MRI scanner allows us to take sort of pictures of the inside of the body. I'm not going to go into the details there, but what I will tell you is that the process is very slow. Now, going through in an MRI scanner, you might have tried it, takes a long time, and that costs a lot of money. So what one wants to do is to speed up that process. And you can use artificial intelligence for that. So here's a paper in Nature that has been quite popular. It was published in 2018 that promises a very new and interesting AI method for speeding up MRI. It was, after it was published, it was also picked up by Nature Methods, which is another outlet under the Nature umbrella. And we learned that AI transforms image reconstruction. And we also learned that this deep learning-based approach improves the speed, accuracy, and robustness of biomedical image reconstruction. Now, the claim about robustness is particularly interesting, given that we know how very unstable deep learning is in general. And that means that we may want to test that claim. So the way the AI works here, I'm going to wave my hands a little bit, but this is the rough idea. So what you see here to the left, that is you or me in the scanner, if you will. But the MRI machine doesn't just take a picture of you like a camera. It produces what is referred to as the Fourier transform of the inside of your body. And that needs to be decoded so that we can make sense of that into an image. And what the neural network does is that it takes this Fourier transform, and what it also allows is that it allows us to take a shorter acquisition time. And it learns miraculously a clever way of taking that information, and then it produces here an approximation. You can see here that the image quality here is not as good as this, but it's still very, very good. And this one here takes about half the time to produce. Now, if it's really the case that this here is stable, I should be able to take tiny little perturbations here. Then it will go through the scanner, and now it will be picked up by the AI, and produce back. And I should be able to see very small perturbations here on the right-hand side. But watch what happens. If you see to the left here, those are the perturbations, and to the right, that's the effect of the perturbations from the AI. And you can see you get a complete snowstorm at the end. This is not stable at all. It's incredibly unstable. Now, you could have asked if this was an inherent problem. In other words, there was an inherent instability in the problem, so every method would suffer from this. But that's not the case. You can use other methods, non-AI-based methods, and they don't suffer from the same issue. So what you see is that you get a very, very unstable reaction from the AI. And this may not be a complete surprise, given that we just discussed how very unstable it is in the case of image classification. Now, you see, this is not one particular issue. It's much more of a universal issue. And I'm going to show you another experiment here with a completely different AI. It's the same philosophy. In this case here, it's 4 times speed up, not 2. And this is created by some very fine researchers at Imperial College here in London. And we do the same experiment. We add a little bit of perturbations here. And if it's really the case that it's stable, we should only be able to see very small perturbations here. But watch what happens. Watch on the left-hand side. Can you see the perturbations at all on the left-hand side? You can see the right-hand side, for which we deform the image completely. Now, when you look at this image here, this is not dangerous. It's a nuisance because a doctor will have to say, well, we just have to redo the experiment. We're seeing nonsense. But it won't kill you. The danger is this. The danger is, can you see the difference now? This is the original, and now I take a slight perturbations. Can you see this thing here? This is what we call an AI-generated hallucination. It has nothing to do with the patient. It's a hallucination that is created completely by the AI. And this is dangerous because it's very hard for the radiologist to deduce that this here is non-physical. This is a false positive. You can have false negatives as well with these AI-generated hallucinations. I'm going to talk about that a little later on as well. So what we ending up with is a phenomenon of instability and AI-generated hallucinations, which is hard to control, and that is quite delicate. For those who are interested, there's a paper on this now. There's actually several papers on this now. It's starting to pick up. This was probably the first one on it, published in May. And when it came, one could get the feeling that there was quite a bit of surprise that this would happen. A lot of media outlets picked up on this because, well, it suggests that AI techniques in medical imaging may lead to incorrect diagnosis. But I do think it's fair to point out that I'm not sure that the radiology community was very surprised. And so Kurt Langlotz, who's a professor of radiology at Stanford, is also the director of the Center for Artificial Intelligence and Medicine at Stanford. And he tweeted immediately after the paper came out that this confirms what many believed about deep learning image reconstruction. In fact, it is very unstable. So now I want to talk a little bit about the phenomenon of AI-generated hallucinations and instability. Because this is not something that you just see where grumpy mathematicians like myself cook up bizarre counterexamples. This is what is actually reported now when we have the competitions with AI in medical imaging. So just as the ImageNet competition became a big deal in computer vision, Facebook has launched what they call the Fast MRI Challenge. And the Fast MRI Challenge is a challenge for research groups to compete and essentially figure out what is the best AI method to speed up and to be able to give you good recovery methods in medical imaging. And a key issue there is exactly what we talked about, namely the AI-generated hallucinations. So this is from the report in 2019. You can also read about this in the report of 2012. And what it says is that such hallucinatory features are not acceptable and especially problematic if they mimic normal structures that are either not present or actually abnormal, just as we saw before. Neural networks models can be unstable, as demonstrated via adversarial perturbation studies. And the 59 here is the paper we just discussed. So this is not mathematical mumbo jumbo. This is actually going on. And I wanted to show you a simple experiment. This is a controlled experiment that we did. And what you see here is the original image. And here is the cropped version. And V1 here is a random Gaussian noise. It's tiny, tiny random Gaussian noise that we add here. And V1 is the worst noise that we picked from drawing 100 times. And here's what you can see. You can see the red arrow points here. And this is an AI-generated hallucination. There's nothing here. There's nothing wrong with this patient. This is a false positive. And you get the same one. V2 is the worst out of 20 draws. And V3 is only one draw. And you can still see that you get this false positive. This is an AI-generated hallucination simply caused from random noise. And you can try this with different methods that are not AI-based, and you can see you get artifacts on this noise, but it's not a hallucination. You can clearly see that these are artifacts, but what is very, very dangerous with the AIs is that they give you something that could be physical, and it looks like this is okay. It's not an artifact. It looks like it could be something, but this is AI-generated hallucinations. And I want to show you a mathematical theorem that just suggests something about why this happens and why it's hard to remedy, just as we talked about this other mathematical theorem that suggests that there are methodological barriers. Because of course, it's not the case that people are not working on this. You want to fix this. We don't want to have instabilities, and we don't want to have AI-generated hallucinations. But the reason why this is not easy is the following. So I'm going to show you, and this, I apologize. If you're a mathematician even, this is hard to read. So I'm not going to do this in detail. I'm going to tell you what it says and what the results are. And what this theorem here says is that if these three conditions here, that may look completely Greek, but if these three conditions here are satisfied, then your AI for image reconstruction will be unstable. It will produce false positives, and it will produce false negatives. And that is the crucial part, because if you want to have an AI which is going to be stable and does not produce AI-generated hallucinations, you need to have a mechanism that prevents these things from happening. And that's not obvious at all. We simply don't know. So we can say with mathematics, this is the reason why this method will produce AI-generated hallucinations. But we cannot say this is the way that it will prevent. We don't know how to design a good method for which this is going to happen. And that is the problem. So right now, there's great promise because these AI methods can produce, in many cases, very good images, but with the caveat that they occasionally produce complete nonsense. And that complete nonsense is not Mickey Mouse. It is something for which the radiologist can interpret either that it takes away, say, a tumor, and it will be a false negative, or it adds something, a false positive, for which can be misinterpreted, and that's dangerous. Okay, I have 5-6 more minutes, and with that, I'm going to wrap up, and I'm going to talk a little bit about the slightly philosophical question, how should AI be used in medicine? It is not the question we should ask if AI should be used in medicine. It's already there. It might be an incredible resource, and it's likely that it will be. But how to make this used in a safe and robust manner, that's not obvious. And for those who are interested, you may want to Google the words IBM, Dr. Watson, and scandal, and you will find quite a lot of interesting readings. IBM is an example where AI have been introduced prematurely without actually understanding what it does, and it had serious consequences. It's not up to me to reiterate that. You can read about it on the internet. But there's a crucial issue here that I want to point out. And that is that neural networks are incredible on average, but they can do very, very unpredictable things. And then one can ask, but as long as it does well on average, it should be fine. The problem here is this. The instability also implies that we cannot trust the confidence of a neural network. In other words, if a neural network says that I am very certain that this here is the case, that cannot be trusted. Now, you could make the argument that, of course, people can make mistakes as well. Absolutely. But in certain cases, humans do have their ability to understand their own limitations. And we cannot trust the confidence of AI in general. And another key issue is that AI cannot really say, I don't know. And when I talk to my radiology colleagues, what they tell me is that when they do diagnosis, for example, on prostate cancer from MRI images, they don't give you the yes, no, yes, you have cancer, no, you have cancer. You get a rating from 1 to 5. 1, if they're very certain that you don't have cancer, and 5 is the number they give you if they're very certain that you do have cancer. Now, what we can do is that we can actually statistically test this and see how good is the human at judging its own limitations. So in other words, when the human says you don't have cancer, is that an accurate statement? And it is. The humans are very good at giving 1s, also very good at giving 5s. When they're certain, they're certain. In between 2, 3, and 4, much more of a toss-up. But in certain cases, the human can actually assess its own limitations. And that's the problem with the AI. So I'm going to end with a little thought experiment to show you exactly this phenomenon. Here's a simple example. And the task for you is to figure out, is it the smallest or the largest square that has the lightest color? In this case here, it is very simple for me, or pretty simple for me to see that actually it is the largest square that has the lightest color. But what I can also see is that this is a problem for which I have a pretty good understanding of where I can be confident and where I cannot be confident. In other words, if this here is very dark and that one is very light, I can say with confidence that this here is going to be the one that has the lightest color. So in other words, I'm pretty good at assessing my own limitations in this. I may not be good at that for all tasks, and by all means, humans are not in general good at assessing their own limitations. After all, we are electing politicians who, some of them seem to have very, very limited understanding of their own limitations, no names mentioned. But the problem is this. In certain cases, the human might be very good at saying, I am very certain about this issue. So if you're now going to get a diagnosis from a machine and it gives you 1, it is very certain that you don't have cancer. But we know that you can't trust that. And you get the diagnosis from a person that says you don't have cancer. And in that case, we know that we can trust this. The question is, would you use that product? And I think this is a part of the debate that is important. It is important for politicians, for policymakers, for scientists like us, and also for you and me who are eventually going to be using these products. And the more we understand and the more we know, the better, hopefully, the product is going to be. And that's my talk about this. I'm very happy to take questions on this. I just want to end with some really promotion about the new book that David suggested. So this is a little bit of promotion of Ben and me, and it's the compressive imaging book. And a lot of the stuff that I've talked about in this talk will be in that book. So those who are interested, please go and buy. And with that, I thank you very much for your attention.
Well, thank you very much, Anders, that's a really exciting and it's a little bit depressing talk, I think, because we've heard about all deep learning and how marvelous it's been, but it seems it possibly is not as marvelous as we thought it was going to be. We have a number of questions for you, and I'm going to read them
Please.
out.
Great.
First of all, could DNNs become better at image recognition if we train them to recognize these edge cases into another class?
Yeah, so we could speculate. And so there is probably a million different attempts out there to fix the problem. And it's hard for me to say that this will not work, this will work, because there are so many different essentially trial and errors in this. My answer to this would be, I don't think that this is going to work. And the reason why is that there's an enormous amount of attempts to do these things out there. None of them have succeeded. If one finds out sort of a slightly different trick and it's going to work, I cannot rule that out, but I don't believe it. And the reason why I say that is that the theorem I suggested, it actually suggests a very general class of methodologies for training it. It doesn't suggest everyone, but I would be surprised if there is a simple fix to this. And if this had been, say, 5 years ago, one could have gotten the feeling that, oh yeah, this is premature, just give us a little bit of time and we'll fix it. But since 2015, there is an enormous amount of attempts of doing this, and there is absolutely no success, and that's why I'm skeptical. But I'm not going to rule it out, but this is my gut feeling.
Right, the next question. How many MRI scans would be needed for accurate diagnosis?
That I'm not 100% sure what that question means in terms of if that means how many scans do we need to be able to train the neural network, or how many scans does a patient need to be able to get this to be accurate. The first one I could say probably something about. The second one is harder for me because I'm not a radiologist. But my understanding is that typically what you end up doing is that you will get one scan, and then that is at some resolution level. And that is a 3D scan, so you get a lot of slices for doing that. And that's what the radiologist will look at. If you need then a better resolution, depending on what the radiologist, the evaluation there, that I'm not the expert to say. But yeah, go ahead, David.
I presume there's only a certain number of MRI scans you can safely have anyway, I guess. So.
Oh, yes, absolutely. So, but I do want to address if this is an issue about the data, the size of the data that you need. And that is an issue. And data starvation is an issue that we're aware of. And one could hope that if you had more data, then you would be able to remove the issue of the AI-generated hallucinations. However, this is also a project that we're working on. I think that we can predict that the current methodology would need so much data that it will be infeasible, not just because we cannot create those data in MRI, it's simply we cannot create enough data in the universe to be able to make this completely bulletproof. That's a speculation yet, but I think we will be able to prove that this is essentially a bottleneck with data. So it's a good question, and I hope that I answered that in the way that the question was intended.
The next question I think I'm going to answer. Can AI be sued for incorrect diagnosis? And I think you'll probably find someone will sue anybody for anything. So yes.
Well, it's a very good question. And I hope, I wish that I was better suited when it comes to legal issues here. It's unclear to me now what happens if the FDA has approved something and that goes on the market and it makes a mistake. So for those who are interested, follow the case with the IBM and the lawsuits that happened there. I don't think that they actually killed anybody because all the trials were essentially shut down when the diagnosis and the suggestion given by Dr. Watson would have killed patients. So I don't think that there were lawsuits about actual mistakes that were done. There are lawsuits about payments and what the product was supposed to do. I don't really know what will happen if the AI had killed somebody and who would be liable for that. I don't know, and I wish I knew. So that's a great question, and I hope somebody can tell me the answer to that.
Next question. Should we not use deep learning, therefore, and should we find new methods?
Well, I think that there is a great potential of deep learning regardless. So I don't think that we will solve the instability problem, but we may be able to have products for which might be not as good in certain cases as the human, but it still might be good enough and better than having nothing. So one project that has been pointed out is really this early detection of diabetes in developing countries for which there's very little resources for doing this. To have a very cheap device, it may not be perfect, it might be a little unstable, it might give you false positive and false negatives, but it might be better than nothing. And there might be also cases for which essentially the human performance is so unreliable that it could be that the AI is as good because the human might be unstable as well. And so I wouldn't say that we should rule this out. I think that the more knowledge we'll have, the better it is. And the question, should we do something else? Likely, yes, eventually. I do think that we'll be able to find a better AI, but maybe not now. It could be that this takes 500 years or 5 years or 10 years. We simply don't know. But I'm happy to have the debate about that we could use deep learning the way it is now, as long as we understand that we can do this in a safe way. And it may not always be safe, and then it will be a debate about, is it still worth the risk?
How would we know when we can and when we can't trust AI in medicine?
That is a great question. That is what I'm trying to say, is that it's unlikely that we will be able, with the current technology, to say that you can trust it, simply because of the instability phenomenon. In other words, if you solve the instability phenomenon, then you solve the issue of trust as well. And if we haven't been able to solve it so far, I'm not going to put a lot of money that we will be able to do it. So I don't think that we'll be able to trust it fully. But as I said, it will be a statistical issue. There might be benefits still, and in cases for which the human may not be that reliable, it might be even better. And the debate about how this should be done, I should say, we're organizing a big workshop on this on the 15th of December at the British Library, where we're inviting top people in the sciences to discuss exactly this. And I think that this is going to be a very interesting discussion, which will not end now and will continue in the future. And the more we discuss it and the more research we get on this, the more we will know. But we will not know this fully.
So a somewhat different question now. Does AI, is AI algorithmically biased against BAME individuals?
BAME individuals.
Yeah, Black, African, and minority ethnics.
It's a
Black Asian, sorry.
Yeah, so it's a great question. And first of all, I don't think I should make a whole lot of sort of expert comments on this, but I think it's valid to have a little bit of thought on it. There has been quite a serious debate about why this happens. And the machine learning community, as I understand, and there's been a debate, you can follow this, Jan LeCun has been a part of this, for which the answer from the machine learning experts will say that it's a problem with the data set that things are trained on. And that is true to some extent, but I'm not 100% sure that that is the full truth. I think that there is much more going on, related also to the fact that we don't know how to trust this. So I'm not really sure that one can deduce that this is just about the data set, but it's too much for me to speculate on. So I don't want to make any scientific claims about this, except saying that this is an issue and it's not solved. And I don't think we really know how to solve this.
Just got time for a couple more questions. Is the issue with diagnostics using imaging not that the technology is based on grayscale bitmaps and the underlying source data? I.e., is the issue in using imaging principle?
Right. So I need to understand exactly what this means. If this means to just make diagnosis based on images, or if it's based on diagnosis based on images from, and say, an MRI machine, because that's different. So,
I don't actually know what the gentleman means, but I guess what he's saying is that are you looking at the image and trying to interpret that and not looking at the source data?
Ah, now I understand. Okay, yeah. So for the MRI, or sorry, for the AI, the only thing that the AI can take in is a bunch of numbers. So that is it's a pixel, a connection of pixels that you have a color code is attached to it. So even if you would sort of put the AI on the patient, the only thing you can do is to take a photograph of it. So for example, for the FDA approved early detection of diabetes, what you do is that you take an image of the backside of your eye, of the retina. And when it looks there at the image, then it sees if the blood vessels are damaged because of the high blood sugar level that you have if you have diabetes. So you can't really sort of have the AI, you as a human, sort of look at a patient. It will always be through a lens in some sense, where you take a photograph and say, here is the information, that's a bunch of pixels, now you make it a decision.
Could we use deep learning for breast radiology?
So
or would that suffer from similar problems?
yeah, so I don't know if this is related, or the person who asked this question may be aware of the big paper in Nature that came out in 2020, January 2020, exactly for breast cancer. And the issue there is that the paper promises great results, that the AI is better than the human, but it only takes one test, and that is yes, no. It doesn't check any confidence. And it's a very fascinating paper. I think there's a certain amount of criticism around it. If you go on the Nature webpage, there's already a Matters Arising paper which criticizes the paper already. You should read that if you're interested. I'm not saying that it shouldn't be used. I think it's a very interesting study, but I do think that we should be aware of the issues we discussed in this talk if we're going to implement this for a large scale for cancer diagnosis.
Right, and a big question to end with: how would you define deep learning? Sorry if it's basic.
Oh, so deep learning, that's a good question. So where does the name come from? So the ideas of having neural networks has been around, I wouldn't say from Adam and Eve, but you know, it's a good 20, 30 years. I would say maybe like 35 years maybe that you've seen. So before 2000, there's a lot of stuff going on in the approximation community. The idea of using deep learning, meaning that you made these neural networks deep, came around later on in the 2000s, when one wanted to exploit the potential advantage of having deeper neural network. And that's the definition. So when you use the neural networks that don't have to be deep, then it's sort of not deep learning. And when you use them that they're deeper, have more layers, that is where the origin of the name comes. And that's sort of the definition of deep learning.
Anders, thank you very much for a very exciting and a sort of up-to-the-minute talk about what is happening today in image analysis and mathematics and AI. We all are very aware that, of course, these machines promise a lot. And I guess now we have to rely on people like you to make them work a lot better. And I hope you have great success in doing that. And thank you very much for giving such a brilliant talk.
Pleasure to be with you.